Hello, everyone. Welcome to our session. We are going to talk about how we are solving the data skew issue at Facebook for our large table joins, along with keeping our I/O within limits. My name is Suganti Divakar. I'm a software engineer in the Spark team at Facebook. Presenting with me is Tony.
Hi, everyone. My name is Tony. I'm also a software engineer at Facebook. I'm working on Cosco, which is an external shuffle service working for Spark workloads.
Today, we will be talking about our skew join journey, where I will describe three solutions that work for us. And Tony will talk about how we integrated Cosco, which is Facebook's external shuffle service, with these solutions. What is data skew? It is the uneven distribution of partition data, and it affects aggregate operations like group by and joins. For example, if we were to count the number of people in each country, we would read all countries' data and group data that belong to the same country into partitions. Each partition is then processed by a single task to obtain the final count. Partitions that contain data of less populated countries would have a smaller size, like partition 1, 2, and 4 on your screen. Partitions that contain data of densely populated countries would have a larger size, like partition 3. In this example, partition 3 is skewed. The task that processes a skewed partition has a larger latency and can slow down an entire query. The effect of data skew at Facebook is further exacerbated because of the scale at which we operate. We have petabyte-sized table joins and terabyte-sized skewed partitions. In terms of task latency, the non-skewed partitions are processed within minutes to few hours, whereas processing skewed partitions take anywhere between multiple hours to days. Skewed pipelines are often latency-sensitive daily jobs with complex tags. Delay in a single skewed pipeline can cause delay in hundreds of downstream pipelines that depend on it. Even though skew affects both aggregate operations and joins, in this talk we will focus only on joins. A little recap on the join strategies that exist in Spark. Shuffle hash join and sort merge join require input data to be partitioned and hence are more prone to be affected by the input data that is skewed. Broadcast hash join, on the other hand, does not require input data to be partitioned, but requires one side of the join to be small enough to fit in memory. Since broadcast join is a mapper type join that requires no partitioning, it is skew resistant. Skew join, which is not an existing join strategy per se, is a hybrid join strategy that combines above strategies in order to mitigate skew. The non-skewed partitions are processed in a usual manner, but the skewed partitions are joined in a way that mimics broadcast join strategy. The mechanism we used to incorporate skew strategy led to the progressive adoption of three solutions, which each deprecating its predecessors. I will describe each solution going forward. The first solution, Skew Hint, is a optimizer's rule-based solution where the user provides us with skew information in the form of query hints. The way they would do that is by using the skewed on keyword followed by a list of column name and value pairs. Once we have the information, the skew information, while planning the query, we split the input data into two parts. The first part containing the skewed keys and the other one containing the non-skewed keys. We then broadcast join the skewed keys and shuffle or sort merge join the non-skewed keys. And finally, union both the join outputs to obtain the final result. Let's visualize this better. Let's take an example of a two-table join, table A and table B, on a skewed column. Without skew join, the physical plan would look something like this. We scan both the tables, partition the data, and perform sort merge join. Since the data is skewed, join task processing the skewed partition takes longer to complete. With skew join incorporated, the physical plan is changed to something that looks like this. On the left, we filter rows that are not skewed and sort merge join them. On the right, we filter rows that are skewed and broadcast join them. Since broadcast join is skew resistant, both these joins complete with little latency. And then we are finally able to union both these outputs. Let's take a look at the pros and cons of this solution. We definitely were able to reduce runtime latency using skew hints. However, this solution required prior knowledge of skewed keys even before query execution. We also had to double scan input data in order to achieve this. This led us to the development of our second solution, which is a runtime skew mitigation based on Spark 2.0 adaptive framework. With this solution, skew detection and mitigation happens at runtime while the query is executing. At the beginning of a join stage, we collect map output statistics of the join's input shuffle data. These statistics contain size information of each partition. We then find if any partition in this input is skewed by applying three simple conditions. The partition size must be greater than a minimum threshold value. It is X times the median size of all the partitions and Y times the 99 percentile size of all partitions. Once we detect that a partition is skewed, we now mitigate it by splitting the skewed partition into multiple subpartitions. The corresponding partition on the other side of the join is duplicated to each task processing the split subpartitions. Since partitions are now evenly sized, the end-to-end latency of this join is greatly reduced. Looking at the pros and cons of this solution, we solved runtime latency along with not requiring prior skew key knowledge before query execution. We also avoided the double table scan problem. However, since this solution is based on Spark 2.0 adaptive framework, we add additional shuffles between joins and joins and aggregates even if a particular join is not skewed. In the third approach, we build and adopt on top of existing skew mitigation solution in AQE, which is the new adaptive framework in Spark 3.0 that was introduced this year. A little recap on what AQE is. AQE is the new adaptive framework in open source Spark 3.0, which also includes a skew mitigation solution as part of it, along with other features. It also allows for runtime DAG changes, which was a game changer for us. AQE-based skew mitigation had some limitations, because of which it did not mitigate skew in our workflows in its original form. AQE skew mitigation supports mitigating skew in two table joins only. It does not mitigate skew in joins that are part of other reducer or mapper operations in the same stage. This includes a skewed join that could also include an aggregate operation or a union operation in the same stage. Since a lot of our existing pipelines fell under this category, it led to us building our first customization. This customization adds shuffles after a skewed join at runtime if it is followed by an operation that requires a specific distribution. Before describing how we went about this customization, let's go over the lifecycle of AQE execution. AQE splits the query at shuffle boundaries into query stages. Each query stage then goes through replanning based on its style stage statistics, followed by ensure requirements, which adds shuffles between operators if required. Beyond this step, no new shuffles can be added to this query stage. The physical plan then goes through sub-stage creation in case new shuffles were added, followed by skew join optimization. In case the skew optimized plan requires the addition of new shuffles, it falls back to the original plan and gets executed. In order to add shuffles after a skew join, if required, we added a new step in the lifecycle, which is the detect skew step. Detect skew finds if the current stage contains a join which has skewed inputs. It marks the output partitioning of this join to unknown, thus forcing ensure requirements to add shuffles after the skewed join if it is followed by an operator that requires a particular distribution. This way, we were able to support most of our skewed pipelines that were previously supported by our older solutions. Beyond this, we also identified further improvements that could be done on above customization. Let's consider a query shape as this one. A petabyte-sized table joined with multiple tables with a single join type. In this case, if there is skew in the first table, the way we would mitigate it with the first customization is by introducing shuffles after each join. The physical DAG would include additional shuffles to mitigate skew. After each join, we would be shuffling petabyte-sized data, which is very inefficient in terms of CPU and I/O. This led us to developing our second customization suited specifically for multi-table joins with the same join types. We split skewed partition in the leftmost table and replicate the corresponding partitions in the rest of the tables for each split. This way, we were able to solve skew in multi-table joins without adding additional shuffles. Now looking at the pros and cons, this solution had all the advantages of the previous solution, plus was more efficient since it did not add unnecessary shuffles when a join is not skewed. Now that I have covered skew mitigation solutions we adopted at Facebook to help with latency, I will hand it over to Tony, who will talk about the challenges we faced integrating the skew solution with Cosco, which helps in I/O.
Thank you, Sugandhi. As Sugandhi already talked about the background and journey of skew mitigation in Facebook, I'm going to talk about the challenges we encountered when integrating skew mitigation with Cosco and how we're planning to overcome that. So, what's wrong with skew mitigation and Cosco together? Basically, skew mitigation splits a skew partition into multiple subpartitions, where each would be consumed by a separate subreducer. The problem here is that it splits partition in mapper boundaries. Well, this works perfectly with vanilla Spark shuffle, as the shuffle output data are grouped by mappers. So each reducer is only required to read data from output files from selected mappers. But in Facebook, we use Cosco as an external shuffle service for Spark. It merges all mapper outputs together so that there are no mapper boundaries in the data consumed by reducer. So the splitting strategy in skew mitigation doesn't work well here. In the example below, each subreducer is only required to read partial data from each file of partition 0, but they're not able to know if the data is actually from its interested mappers until they iterate through each file. Before we jump into the solution, let me give you a very short recap on Cosco. I believe a lot of you guys have already heard about Cosco before. If you're not familiar with it, there was a tech talk about it, which was held by my colleague Brian in the Spark Summit last year. Basically, Cosco is a shuffle as a service currently serving the Spark workload in Facebook. It's mainly focusing on the I/O efficiency to address two issues. The first one is write application. The second is small I/O. It also sometimes improves job latency, but that's just not our focus. In short, Cosco groups shuffle data into files by partitions, while the vanilla Spark shuffle groups shuffle data into files by mappers. Each mapper streams the shuffle data to the corresponding shuffle service instance based on partition ID of the data. Cosco shuffle service has a write-ahead buffer for each reducer partition, so it merges data from different mappers and flushes them to disaggregated storage. Therefore, each reducer is only required to read from those files dedicated for a particular partition. Also, data could be duplicated due to various reasons, and the duplication is also performed on reducer side. Other than the components I just mentioned, there's also a dedicated metadata service for metadata registration of shuffle files, which would be retrieved by reducers later. As I mentioned earlier, to make Cosco with mapper splitting boundaries, each subreducer has to read the entire data set of the skew partition, and then filter out those data from uninterested mappers while iterating through the entire data set, and only consume from those interested mappers. And as you can expect it, this is very inefficient since the skew partition data has to be read multiple times, that each subreducer has to read all data. And of course, this doesn't work very well. In the worst case in Facebook, our most heavily skewed partition could be up to a few terabytes, which requires thousands of splits for just a single partition. And that means the partition would be read thousands of times. And we found out that the majority of the time would be spent on disk I/O in a case for such jobs. So since Cosco groups shuffle output by partition, and each partition could have a large number of files, it is natural to just ask ourselves, why can't skew mitigation split skew partition based on file boundaries? This is a very tempting idea, but before we jump into the design, Let me explain why this is actually not a trivial problem. First of all, let's classify three terminologies I will use frequently in the rest of the talk, namely record, package, and a chunk. So record is the unit of a data row, and the multiple records being buffered would make up a package, which is the unit to be sent from mapper to Cosco Shuffle service. And the multiple packages buffered by Cosco Shuffle service make up a chunk, which will be flushed to disk as a file. So the main restriction to perform a file boundary splitting is because of duplication. Basically, the shuffle data from Cosco Shuffle service is likely to contain duplicated records due to packages resent by mappers, which might be caused by various reasons. To deduplicate such packages, Cosco reducer client would either perform a merge sort or keep a hash map to achieve this. But either of them requires each reducer to read all data generated by the mapper of that partition. Otherwise, if the output of mapper of the partition is partially read by multiple reducers, none of the reducers would be able to tell if a row is duplicated in the data read by others. Because of this, the file set assigned to each subreducer has to have no overlapping of mappers with each other, which is just not feasible. For example below, subreducer 0 is assigned to read from file 0 and 1. But since file 0 and 1 have mapper overlapping with files 3 and 4 respectively, both files 3 and 4 have to be read by subreducer 0 as well. Since Cosco randomly merges results from different mappers, each subreducer will be likely to end up with reading all files of the partition again. So, to make Cosco work with file splitting boundaries with skew mitigation, we need to find out a new way to deal with duplications. Basically, there are two ways a duplicated record could be generated. The first one is caused by mapper failure and restart. We deal with this by assigning unique IDs to different mappers. Even for a restarted mapper, it has a different ID with the original failed one, and each record is appended with its mapper's unique ID. When a reducer starts to consume data, it knows the unique IDs of all succeeding mappers. So any records associated with IDs of failed mappers will be dropped. Therefore, duplicated records caused by mapper failure will not be a blocker for us to splitting in file boundaries. The second cause is because of network issues that a mapper fails to receive ACK messages from a shuffle instance after timeout. Thus, the mapper has to resend all packages waiting for ACK messages. And all records within those packages would be likely to be duplicated in files since they are sent twice. We call such packages suspected packages, which is observed from mapper's perspective that each packages are likely to be duplicated. Note that a suspected package is not necessary to be a duplicate package, but a duplicate package is always a suspected package. So, if we can identify all suspected packages and parse the info along from mappers to corresponding reducers, would that help on duplicating packages? The answer is yes. Each mapper would bookkeep all the suspect packages it observed, basically by adding all those packages being resent to different shuffle services due to missing ACK messages. And such packages would eventually be ACK'd along with a chunk ID. The chunk ID would be a unique identifier for the authorized file containing the records of the suspected package. So each mapper keeps such mapping from the suspect package IDs to their authorized chunk IDs of each partition. When the mapper is done, it will report those suspect package info to Spark driver. And of course, Spark driver would aggregate all the suspect package infos from all mappers. On the reducer side, it will first talk to our metadata service to fetch a list of files to read from the partition it is assigned with. Since we're splitting in file boundaries, subreducers of the same skew partition would have non-overlapping files to read from. Meanwhile, each reducer will also get a suspect package mapping info from that partition from the Spark driver. When iterating through the records of assigned files, the reducer will check if it comes from suspect package. If not, we're just confident that this is not a duplicate package at all. Otherwise, the reducer would only accept the record if the file chunk ID matches with the authorized chunk ID in the mapping. So in the example below, both chunks containing the same record from mapper 3, packages 4. But since the authorized chunk ID is 15, the record would only be read by subreducer 2 and dropped by subreducer 4. What if a file chunk is lost? In original Cosco, since each reducer has to read the entire partition data, so the data to be read by the reducer is deterministic. We only need to restart the mapper to regenerate data of the partition for the lost chunk. And the new reducer will be restarted to read all the data of the partition again. But with skew mitigation splitting in file boundaries, the data to be read by each subreducer is non-deterministic. This is because the restart subreducer will only read a subset of regenerated files, and the regenerated files are non-deterministic since Cosco Shuffle service merges mapper outputs randomly. So simply restarting the subreducer would be a mess up here. Therefore, when a chunk loss is detected, Spark driver would broadcast all subreducers of the partition to fail them all. And once the partition files are regenerated, it will restart all subreducers of the partition again. But it is also worth mentioning that this is a very rare case because Cosco uses RS encoding for shuffle chunks. Putting it all together, the motivation of this change in Cosco is to make Cosco with Spark skew mitigation by splitting a skew partition into multiple non-overlapping file sets that each subreducer will be assigned just one of them. And to achieve that, each mapper will keep tracking of suspect packages along with authorized chunks and report suspect package infos to Spark driver when finished. Once the mapper phase is done, the Spark driver will detect skew partitions based on mapper status and split skew partitions based on file boundaries of each partition. Each reducer would fetch a list of chunks to read, along with the suspect package info of the partition. It would accept a record of a suspect package only if it is read from authorized chunk. As the summary of our talk, today we discussed how we improve the runtime latency of pipelines by gradually solving the skew problem of our large join efficiently, namely skew hint, runtime skew mitigation, and also customized adaptive query execution skew mitigation. We then discussed the importance of Cosco for I/O efficiency, the techniques involved in solving the challenges we faced while integrating adaptive skew mitigation with Cosco by splitting skew partitions into non-overlapping file sets. We hope you found the session useful, and thank you so much for listening.